and I'll be basically taking you through data grids. In general, we'll have a look at the capabilities of Oracle Coherence in a sort of run through, and we will have a brief look at when and why data grids are used. So the first question we're going to look at is data grid just a cache? We're all familiar with data caches. Data caches aren't new. As developers or architects, we've spent a lot of time tuning and using caches. For example, if you use Hibernate or JPA, then there's a second level cache or a session cache in there. Session cache will provide you with storage of objects across or during a transaction, and the second level cache will store objects across transaction boundaries. And there are many other open source caches, for example, Cache. A while ago, there used to be something called OS Cache. And typically these caches are used to store database data. I mean, fundamentally, the only reason you would use a cache in any architecture is to reduce latency. Essentially, caches are used to move the data closer to the processing to remove latency when accessing typically database data, but it could be any sort of data. For example, you get caches on CPUs that store frequently used data very close to the computation, so you don't have to go out to main memory. We can get caches in many architectures, but in general, if you keep it in your mind, a cache is only typically there to reduce latency in an architecture. So if you're going to have a cache in your application, so you think is an area which is slow and requires some caching, why don't you just create your own cache? Obviously, if you do your own, then the benefits are it's very, very simple to write. You can just take a concurrent hash map, store some data in it with a get and a put, and that will allow you to create your own local cache. And many people do this in their applications. So you see, when we go into the field, we see a lot of homegrown caches. And if you really wanted to be advanced, you could wrap your cache in JSR 107, a cache API, and use an industry standard, or it will be an industry standard at some point in the near future. However, if you start on that road, then there are many challenges ahead for you. For example, caches must support at some point some cache eviction. Cache eviction is where, in order to stop your cache getting too large, that you throw data out based on some algorithm which could either be least recently used or some time to live or some other thing. You're also going to have to program a way to load data from your data store into your cache. So you need to form some cache loading, so some write-through or read-through or mechanism, and you may want to also prefetch data from the cache, from the data store into the cache to allow you to warm the cache up, so to reduce the latency even further. And again, once the data gets stale, you need to create a way to refresh that cache. And also, one of the key issues that we see is when people have created their own cache, that when you start putting this application into a clustered application server, then there are difficulties in that. How do you keep data in different nodes of your application server cluster in synchronization? Sorry, I just hit the wrong button. So think long and hard before you create your own caching strategy. So we mentioned, if you do create a cache, how do you create a clustered cache? And we look at some of the problems with clustering cache data in the next section. So here we have, we've created our cache. We have an application. We're scaling out by adding 2 nodes onto a cluster. The problem we have in managing cache data in this way is cache coherence, essentially keeping the cache in sync, hence the name Oracle Coherence, as it achieves this capability. So imagine the scenario. Our application wants to get at some data. Most caches are essentially key value stores. So you use a get with a key and return a value. So we do a get on our cache. We load our entity from the data store, and we sit there, and that entity sits in the cache. So the next, on another node, we do exactly the same. So now we have, across our 2-node cluster, we have 2 copies of object B sat in the cache. The problem occurs, essentially, what happens when updates are the main problem with a clustered cache. So say we have 2 entities sat in the cache, B1 on both nodes. The problem we have is what do we do when we get an update to B1 to make that object into B2? So what we have to do is we need to keep the cache in sync. There's 2 mechanisms to do that. The first is update replication, which we're showing here. So as we put B2 into the cache and do an update, then what we have to do is we have to replicate it across the cluster to keep the cluster coherent, and that's called cache replication or update replication. There's an alternative mechanism that you could use in your cache, which is essentially update invalidation. So what the difference between update invalidation and update replication is that update invalidation will in some way throw away the data that's in the other node. So when we do an update on B1, our cache is in an inconsistent state. So we have B2 in the left-hand side and we have B1 on the right-hand side. So if an application was accessing different cache nodes, we would get inconsistency. So in update validation, what occurs is we send a message across our cluster, and that will invalidate the cache, essentially throw out the inconsistent data, leaving us with consistent data on the left-hand side. And then as further requests would come in from the right-hand side, then that cache would be empty and we would retrieve the data from the data store. Hence, we would always see the same value, but at a cost of some latency. So the problem we have with replication or invalidation is what happens in writes as you scale your cluster out. So if we have we scale out 4-node cluster, we put some data into the cache. So we put entity into the cache B. What we have to do now is we have to replicate that data across 4 nodes on our cluster. And if we went to 8 nodes, we'd have to replicate across 8 nodes, 10 nodes, 10, etc., as the cluster grows. So, and this has quite a cost. There's 2 ways we could do this. We could do it synchronously, in which case, as the data is written across the cache, the application wouldn't return until the data is fully replicated, and therefore the system is totally consistent. Or we could do it, as is shown in this sort of little animation, asynchronously. So we put some data in the cache, our application returns, and then we asynchronously replicate across. So for writes, full replication is very, very non-scalable in that performance drops as you add more nodes into the cluster. So the way large-scale caches like Oracle Coherence get around this is through partitioning their cluster. So again, if we look at our 4-node cluster now, cache partitioning splits the cluster up into different key sets, and each node within the cluster will earn a certain set of the key. So in this case now, what happens when we put our object into the cache is that it sits in one of the nodes. So in this case, we're on the furthest left-hand side node. Our entity sits in that node, and then any application that was accessing the cache, for example, could hit any other node in the cluster. And what Oracle Coherence will do in this case is it will pull the data across the cache cluster and return it to our application. So through cache partitioning, we gain both a coherent cache in that all applications, no matter which node they're talking to, see the same consistent view of data. But we also, we saw when we put the data in, we don't hit the replication overhead of a fully replicated cache. So cache partitioning essentially scales better than fully replication when you look at cache topologies when you move into clustered caches. But cache partitioning gives us a slightly different problem, which will come in a second. The thing to note about cache partitioning is when you put data in the cache from an application, so in this case our application is talking to node 3 and it puts data in the cache, the data may not actually sit or be stored on the node where your application put it. Due to the key partitioning that will occur, different nodes own different key sets, and that's typically transparent to the application. So when we put our data in, the cache and clustered cache underneath may move that data around and put it into a different node in our cluster. As we said before, the problem with cache partitioning is high availability. So if we put, get back to the state we're in before, where we had an entity in the left-hand side, in order to make that entity highly available, in the case of a node failure, what Coherence will do is it will replicate a configurable number of copies of your entity onto different nodes in the cluster. So in this case, we have a single copy. So we go back. So what happens is, as we put data in the cluster, Oracle Coherence under the covers will create a backup of that piece of data, and the backup of that data will be on a different node in our cluster. And for Oracle Coherence, that backup could also be in a different, it's clever enough to make sure it's on a different machine. So if you have two JVM nodes, Coherence nodes running on the same physical host, then Coherence will ensure the backup's on a different host in case of host failure. It can also be configured so that the backup is on a different, say, server rack in the data center to give you high availability against a rack failure, for instance. So now what happens is, if our node crashes, we still have a copy of the data. And in fact, what will happen is the node that is the primary will detect that the backup node has disappeared and will create a replacement copy on a different node in the cluster. So in Oracle Coherence, it's very dynamic. So loss of a single node will cause a repartition, and the data will get redistributed across the cluster. So we've seen that creating a simple cache using concurrent hash map is simple, but then when you need to start clustering that into large scale application server clusters, then clustering becomes an issue. We've seen that fully replicated clusters don't really scale for writes, in that we have to write to as many nodes as there are in the cluster, and that takes time, and the more nodes we add, the longer that time is. So Coherence does support fully replicated clusters, but it also supports partitioned clusters or caches. And in this case, partitioned caches, we store a single entity on a single node with a backup somewhere else. Now in Coherence, the number of backups we have is configurable to you depending on your requirements, really, for high availability. So the big key really about partitioned caches is partitioned caches give us linear scalability. Essentially, no matter how large the cache is, worst case network hops you'll get when you put data into the cache is 2 hops. So if we go back to the previous slide, if we put data into the wrong node, then, for example, the node that's holding the data is the left-hand side. If our application was accessing that data from the middle node, that doesn't store the data, so we'll get a network hop into our cache and a network hop to pull the data across the cluster, as we saw before in partition caches. So worst case, we get 2 hops for read. And also for write, when we do an update, the worst case is that we hit a node that isn't going to store that key, and Coherence will move the data across the cluster. So worst case, we get 2 hops for write as well. And that's the same whether we have 10 nodes in the cluster or 100 nodes in the cluster. So it gives us essentially linear scalability. Partition caching like Coherence also gives us high availability, as we've seen. We can create a configurable number of duplicates depending on how much we really want to make sure that we don't lose any data in this cache. So we get linear scalability, we get high availability of our data. We also get location independent access. As I've shown in the animations, it doesn't matter which node in the cluster the application is talking to when it does a get. Oracle Coherence will pull the data over from the correct node, the one hosting that data, and send it to your application. So that gives Coherence a big advantage over, say, client partitioned caches, in that you can add more nodes into Coherence elastically, and it will, it doesn't affect your application. Your application still talks to the same nodes, and Coherence will find the data to find the entities based on the key. So the grid in Oracle Coherence essentially knows where the data is. But another key point that's often forgotten in partition caches is that the more nodes you add, the more data you can store in memory. So just as a simple model, if we look at a large cache, so here we have 21 nodes, which is a fairly large cache. If all 21 nodes had full of data, then how much would we actually store? So we did a quick calculation. So if we say we were taking and using 21 Amazon extra large memory instances on Amazon AWS in the cloud, then we also put 3 nodes, so as in 3 Coherence nodes per instance, and we'd run each Coherence node with around 4 gig of 64-bit JVM heap to essentially keep the garbage collection times into a reasonable level. Then we would have 63 Coherence nodes within that 21 machines, and assuming that would give us effectively 4 gigabits per node. 63 times 4 gives us 252 gigabytes of JVM heap available. Now, assuming you could use most of that heap, and we configure 1 duplicate for high availability, so the more data we add in, we have to halve the amount we have. So we could put essentially half of that 252 gigabytes of data we could actually store as physical Java entities. So that gives us about 125 gig into a grid of that size. So you can see then how partition caches allow us to actually scale out into large scale client server data caches in Java. And as we've seen, those data caches will give us linear scalability even in this 63 Coherence nodes. Doesn't matter which node you talk to, you will only jump across. Coherence will only pull the data across from the node that stores it. So there's only going to be 2 network hops, even though we have 63 Coherence nodes. Similar for updates. Also, it doesn't matter which node we talk to, we can still access the whole of the data set with that linear scalability. And given that we've had a single duplicate, then we've also got high availability. And the cost, from an Amazon perspective, is not that high. So this is essentially where we're going. This is what makes a data grid over a simple cache. Say it's like a fully replicated EH cache or something like that, or a web session fully replicated cache. Oracle Coherence, as well as storing that data in memory on the JVM, can also store and passivate data from the cache onto a local backing store. For example, an NIO memory map file or Berkeley DB local storage. And the reason you may want to do that is if, say you want to increase the size of the cache beyond what can fit in memory, then essentially Coherence can start passivating some of that data off to a local storage. Now you're assuming when you're going to configure that the latency, if you remember, the only reason you use a cache is for latency. You're assuming when you have configure a backing store that the latency of that backing store is much lower than the latency of going back to the original data store, assuming you have a relational database behind your cache, behind your Coherence installation. And this sort of storage in Oracle Coherence is optimized through a capability that's called elastic data. So elastic data is essentially a way of passivating data out onto backing store, which is SSDs. And it's a highly optimized backing store mechanism within Oracle Coherence, where, in the similar as before, data is written off to SSDs, but it's written into a journaled file system, so that it's extremely high performance file. And if it's running on SSDs, it's extremely high performance, and therefore it's much more likely to have very good latency. And in this case, all keys are actually stored in RAM, and it's just the values that are stored off into backing stores on SSDs. And this allows you to scale out your data grid to store even more data in it than would be possible just in JVM heap. So if we think of taking this to its logical conclusion, and there's some customers that we work with that do just this, if you can, for example, in this diagram, you can make sure that your duplicates are on separate server racks in the data center, and that potentially what you do is you split your cluster across multi-data centers if you have very good one capability. Then what you have essentially is very, very highly available in-memory data set. And if you have a very highly available in-memory data set, then the question is, actually, do we need the backing store database at all? And this is what essentially is a data grid. A data grid is a database of record for your application without necessarily a database. Now, many of our customers, especially in finance and gaming industry, will actually run their Oracle Coherence grids as a database of record. And the way to do that is that a couple of ways they would do that. One is they would be able to reload the cache, essentially. If for some strange reason we lost 2 data centers, or we lost or we had to power down the whole cache and we lost all our data, which would be an incredibly rare occurrence, then they can essentially reload their database, their data grid, their Coherence grid, from stored data from some form, either from a database or from data feeds or that they're recording or whatever. So typically in gaming, this may be sort of market data on betting, or it could be in finance, it could be trade data. So there'll be some record. It may take a while to reload the grid, but worst case we could do it. And so many applications will run large-scale in-memory grids purely for applications to talk to without need for a database. The other model we see quite a lot is that the database is business audit, essentially. So what we mean by that is in Oracle Coherence, we have a highly available data store, essentially. So we store our data in the grid, and many applications, a lot of the data they store is not really business data, in the sense that it's not long-lived data. It's only stored in the database so that we can build ourselves stateless web services, stateless web applications. For example, in gaming customers we work with, it may be they're doing online poker or something, and we're storing in the database who's sat at which table in the poker, and we store that in the database so that if we have a large-scale application server cluster feed for serving the user interface, then to make our service stateless, we push all the data in the data store, we retrieve it on each request and build our website, and we push it out to the customer. Now, in a coherence model, what we do is we'd store that semi-transient data in the data grid itself. And it's only occasionally we'd write data out to the data store, and that data would typically be real business data, for example, financial transactions. So when people's positions, people's bets, etc., or people's cars that they currently have are not important to be stored for long-term audit purposes. But when someone actually wins or places a bet and takes home some money, for example, then that obviously needs to be written away for business purposes. So what we can do is write objects out of the grid periodically, either using write-behind processing or, as we see later, eventing, to determine when we write something off to the relational state store for long-term persistence. So as you move into these large partition caches, it's very possible to create totally different architectures. We're not just talking about first and second level caching. So an Oracle Coherence grid is so much more than just a level 2 cache on your database, essentially. There's a lot more you can do. We can store a lot of data in there. We can access it very fast. And that's just when we're talking about partition caches access through the usual map, sort of get and put APIs. But there's a lot more in an Oracle Coherence grid than get and put. So how about computation on the grid? The problem with computation on a data grid or on a traditional partition cache is, example, you have a partition, you have 4 nodes in a cluster. You want to do some post-processing using the cache API. So what we do is we do lots of gets. We pull the data over to application. So you write some Java code, it just get, as we'll see in the next webinar. And what you're doing then is you're pulling the data across the grid. And that can be expensive from a network perspective. For example, if you need to access, say, a 200 megabyte data set during that processing, then you're going to have to pull that 200 megabytes across the data grid. And then when you're finished updating it, you're going to have to push that 200 megs of data back across the data grid. And this can be very expensive on a network. Data grids are essentially network applications. Tuning the network is where you get your benefit. So to solve that problem, there's a couple of ways, and we'll walk through some number of ways you can solve that in Oracle Coherence. One of them is a near cache. Now, a near cache is effectively a second level cache within Coherence. So if you do your processing, you will still have to pull all that data across the grid. But what you do is you store it in a local cache. Your application, it may be like effectively your web session, and then next time you need to process it, the data is local to your application, and you don't have to pull it across the grid. Essentially, you've created another level of caching. And Oracle Coherence will keep that near cache up to date. So when updates occur, the objects that you're on the cache will essentially be either invalidated, or you can configure them to be replicated into there. But that's sort of a very cache-oriented manner of solving this problem. So what about querying as well? So in querying, in Oracle Coherence, it does support a query language which is called CoQL, which is similar to SQL. Well, it's more similar to ObjectQL, like in JPA. But in Oracle Coherence, when you execute a query, it actually sends the query across the grid rather than pulling all the data, which would be all the data, to your query processor and accessing it there, which would be very expensive on the network. Oracle Coherence will push processing out onto the grid, execute it locally, bring back the results to you, which is obviously much more efficient, taking the query across the grid, executing it locally in parallel, so using all the multiple CPUs as well, and bringing that back is much less expensive on the network. You can also create in Oracle Coherence something called a continuous query cache. And what that essentially does is you set a filter, which is like a query. Coherence, like in a similar way to the near cache, will pull the data and it will sit in the continuous query cache. And as updates occur, Oracle Coherence will keep that continuous query cache up to date. So for example, if an object is updated and it now matches your query, for example, say you had a query, so age greater than 26, one of the entities is age of 27, someone updates it to say 26, then Oracle Coherence would detect that and keep this local cache based on the filter up to date. Like that, and that can either be done synchronously or asynchronously. And then the next time you access that, it would be processed locally. And this is all, the continuous query cache is essentially built on Coherence event subsystem. So Coherence has a generic event subsystem where you can set filters that your class is interested in. And then when any events occur, for example, in Coherence, like an object is updated, then Coherence will notify your what is called a map listener. So for example, if our map listener was interested in inserts, when an object is inserted, then Coherence will notify that map listener, and then it can do whatever it likes in your code. So essentially it's just a callback into your Java code. So the event system allows you to build different applications using totally event-driven applications. There's another capability in Oracle Coherence called in-place processing, and this essentially is to solve that problem of pulling all the data across the network. So instead of pulling the data across the network, when you want to do some processing, you can actually send the processing across the network where it will execute locally on the keys that match. So in later webinars, we have a webinar to show you the code behind this, but essentially what happens is you create an event processor, you give it a filter, which is a sort of a query of the objects you're interested in. You then call execute. Coherence serializes your code processing object across the network, and it executes on the partitions where those keys are living locally. So you're accessing the data locally in memory speeds. You then return your results back to your application. So in-place processing solves the problem of just a straight cache of what you need to do if you need to process large quantities of data. In Coherence, you can process that data locally. So that gives you many advantages. It gives you extreme performance because the data you're accessing is local to you in memory speeds. It gives you huge parallel capability because you're obviously using the power of each machine that's underlying each one of those cache nodes and the CPUs on there. So if you have 4 nodes, you're using potentially 4 CPUs or 4 quad-core CPUs, or depending on whatever hardware is underneath. And this gets used a lot in, for example, financial calculations or risk calculations. If you imagine a cache full of positions and trades, and you want to place an order, and you need to calculate the risk that order will have. Well, the data that needs involved in that calculation may be spread throughout a large-scale Coherence cluster. And to pull all that data locally to do the risk calculation would be quite expensive on the network. But to push your risk calculation out to run in parallel gives you in-memory speeds and parallelization. And we've seen some customers this go down into sub-second response times on these large complex risk calculations on large quantities of data. Another final feature of Oracle Coherence is Coherence Extend, and what this essentially is it turns your big data grid into a client-server cache. So Extend clients talk to a specific node in the grid, and they are clients to the grid in a client-server model. So the clients in Extends essentially have remote access to the cache, but they can use all the capabilities that, say, an embedded Coherence node can use. So they can use filters, they can use remote processing, they have near caches, in-place processing, they can get events, they can use continuous query caching. But another advantage of Extends clients is that it actually supports .NET, C++, and Java. clients. So if you need to integrate your application into .NET clients or .NET websites, then you can take your Coherence Grid and use those clients. So what are the most common use cases for data grids that we see? Well, this is actually from Forrester research, quite old Forrester research. So some of the typical applications that we see, the first is obviously session data. There's a number of advantages, especially if you use something like Coherence Web, which is a basically inbuilt session cache for WebLogic or Glassfish. If you put your session data into a data grid, then there's a number of benefits. One is you can refresh your application server cluster without losing any of the session data as it's stored in the data grid. You can also scale out your session store in the same way we've seen. We can scale out Coherence, so we can store large quantities of session data out in the data grid. We can also make it accessible to other applications if it's out in the data grid. Some people use it for staging static or transient web data, which is sort of fragments of data. Much large-scale caching of shared application state or reference data is another common use case. Obviously, caching of results from database queries, there are capabilities in Coherence to do right behind, we haven't got time to explain, but right behind integration with relational databases, which is where you essentially asynchronously write out to the relational database, or write through, where you can, Oracle Coherence can use JPA provider to write the Oracle Coherence entity straight through into your relational database to keep it in sync. You can do write through and read through, and that's a common use case. Another is, like we mentioned, compute-intensive jobs and large-scale data. So these are where you need fast response. So we're not talking MapReduce H-based quantities where we're talking response times in minutes or hours. These are where you need to use get a response of large quantities of data in a few hundred milliseconds, such as risk calculations or trading position calculations, or anything that you need a fast response. So if we put it all together, a typical architecture we see is where we'd have behind here a relational database. We have a large-scale data grid. We have a bunch of J cluster nodes with a load balancer in front. And what we can do, if you look at the basic case, is obviously, go back on that one. Basic case is obviously the J cluster nodes just accesses data from the grid using get and put. But if we build up events, and we've got some other presentations on our website around this, and also some demos, which we did at Java 1 around WebSockets. If you take the idea of the events capability, we sort of described briefly where you can set a filter on objects that you might be interested in as a map listener. Then you can register a map listener and, oops. I messed up there. You can register a map listener, and when an update occurs, you can fire an event which triggers an event which goes to your cluster node, which can be pushed down WebSockets. So that's another way of accessing it. So what can the data grid do for you? So Oracle Coherence essentially is a large-scale partitioned cache with compute capabilities, with eventing, in-place processing, parallel querying, and it will essentially give you extreme performance through reduced latency. You can move your data close to your processing, and that can either be cached relational data or in parallel compute, and therefore can reduce round trips to latent data stores. But it can also give you that parallel processing, so it's distributed processing with a MapReduce-like API, distributed query processing. It gives you extreme scalability, so we have constant time for reads and writes. So worst case, as we saw, we have 2 network hops. The more data you store, the more nodes you add, the more data you can store. So you can store large data volumes in the grid. You can add more nodes, and as you add more nodes, for instant response to load, etc., you get more storage, and cluster will rebalance as you add and remove nodes. We get extreme availability. There is no single point of failure in the Coherence Data Grid. The duplicates will prevent data loss, and we can obviously configure how many duplicates we have. We can actually configure right behind, which we haven't touched on, which will store data in the data grid, and when the database comes back, if the database is down, you can then write that data asynchronously through to the data store, so it can actually decouple your application from database availability. And it's self-healing, so taking a node out, it will rebalance and it will restore duplicates across the cluster, as we saw in some of the animation. So on the coherence side of things, what can C2B2 do? So very quickly, C2B2 are specialists in large-scale JE application servers. We are leading independent middleware experts. We provide coherence architecture and design services. We can provide production configuration for your coherence cluster, so we can make sure it scales, is tuned correctly, and if you have any problems, we can do troubleshooting work as well. We also provide 24/7 operational support, so we can, if you have a coherence cluster in production, C2B2 can provide second line, third line support to your ops team on coherence if there's a problem. And if you're looking at purchasing coherence in the future, we can provide license advice, and we can resell Oracle Coherence. So that's the end of this webinar. We have another couple of webinars in the next couple of weeks, so one a week. One is looking at simple API, so essentially we'll build a simple coherence application and show you how to use the Java API to coherence. And the other one will look into the parallel processing capabilities in coherence, and we'll show you how to use those to write parallel in-place processing capabilities. Thank you very much for your time. And if you want any more information, go to our website. We have quite a few presentations. There's also a demo on our blog of using WebSockets with Oracle Coherence, which we did at Java 1. So thank you.